Now let's walk through an example to see how we may apply all the notations and formula to construct the optimal simplex table. So in this example, we are given a linear programming problem, and then we're also given the information that in the optimal table, the optimal basis consists of these basic variables, x2 and s2. Based on these two information, we need to be able to compute the optimal table. First of all, convert the problem into standard form. Because both constraints are less than or equal to, we put slack variables plus s1 plus s2. And then we are going to use all this notation and formula to construct the optimal table. So for the constraint part, we know that the basic variables are x2 and s2. So first, because we need the B inverse, we start by defining the B. So x2, the column for x2 is 2 and 1, and then the column for s2 is 0 and 1. So that is our B matrix. From here, you perform the inverse of this B matrix, and then you get this B inverse. Once we have B inverse, we may calculate the constraint part on the left-hand side and the constraint part on the right-hand side. Okay, so x2, s2 are basic variables. So for the non-basic, we need to calculate the columns. So non-basic are x1 and s1. For x1, we get the column of a1 is 1 and 2. So here the column 1 and 2. And then B inverse times a1. So this is the column of x1 in the optimal table. And then for s1, do the similar thing. A for s1 is 1, 0. And B inverse times A for s1 equals this. And then for the right-hand side part, the small b is 6 and 8. So we get the optimal table value for the right-hand side is 3 and 5. And then if you ask why don't we explicitly compute the columns of x2 and s2? Well, because they are basic variables in the optimal table, the value must be canonical. So x2 will have the value of 1, 0, s2 will have the value of 0, 1. So they look like this. So for x2, the value is 1, 0. For s2, the value is 0, 1. For the other one, we get the result from here. So this is the column for x1, this is the column for s1, and this is the right-hand side. So that's the rows for the constraint part. For row 0, other than B inverse, we also need to have CBV. So the CBV is 4, 0 because this is our basic variables, and then the cost for x2 in the original problem is 4, and then the cost for s2 in the original problem is 0. We don't have s2 in the row 0 of the original problem. Okay, so CBV equals 4 and 0. And then we calculate CBV B inverse, and this is our result. Once we have CBV B inverse, let's calculate all the coefficients of the non-basic in row 0. So the coefficient of x1 in the row 0 may be computed by CBV B inverse a1 minus c1. So this is CBV B inverse, and then a1 is the column of x1 in the original problem, so 1 and 2. And then c1 is the coefficient of x1 in the original problem, which is 1. So the result is 1, and then we may also compute the coefficient of s1 in the optimal table. We may use CBV B inverse to do that. So we get the first coefficient is 2, so that is the coefficient of s1 in the optimal row 0. For the right hand side, we may compute it using the formula CBVB inverse times small b. So this is our small b, and the calculation result is 12. Again, we do not explicitly compute the row 0 of x2 and s2 because they are basic variables. For basic variables in the optimal table, their coefficients must be 0 in row 0. So this is our complete table. So the coefficient of x1 is 1, the coefficient of s1 is 2, and everything else is 0, with the right hand side of row 0 equals 12. Good. So we've seen how we may use all these notations and formula to construct the optimal simplex table of a linear programming problem. While that by itself is cool, it doesn't seem very useful, right? So next week we are going to use all these notations and formula to perform sensitivity analysis in the linear programming problem that has more than 2 variables. Because if we only have 2 variables, we may perform the analysis graphically, but then when we have more than 2 variables, we will see that we are going to use all this notation and formula to perform the analysis. So that's what we're going to talk about next week. See you and thank you.